Welcome to video number 3 on use substitution. Very, very, very important for extension 1 to make sure you know how to do these. They are not difficult once you learn the process. So if you find these difficult or you find that you can never get it down to what it needs to be, practice it a little bit more. I promise this is definitely part of the doable marks in an extension 1 exam. So I've written down here, to start with, we're going to look at the indefinite integrals, okay, so where we don't have bounds, in other words. Now I've written 4 steps, 4 easy, basic steps to do. Step 1, differentiate u with respect to x. Step 2, solve for dx equals. Step 3, sub in u and sub in dx. And step 4 is integrate. Now in extension 1, not so much extension 2, but they give you what they want you to use as a substitution. So let's go with step 1. I'm going to differentiate u with respect to x, or whatever value they're using, okay? When I do that, I just get 2x. Step 2 then says, okay, now rearrange that for dx equals, which means I'm going to have, if I take my dx over, bring that back over, I'll do it in 2 steps for you for now. Oops. But hopefully you can just jump to that step straight away. Okay, that's step 2. Now it says sub in u and sub in dx. So now I'm going to get the integral of, my 2x doesn't change, but then I have the square root of u is x squared plus 1, x squared plus 1, so that makes that u. And my dx is now du on 2x. Now every single time, one of 2 things will happen here. Either any x's remained in the question will cancel, which you can clearly see now. I'm dividing by 2x, timesing by 2x, so they cancel, which is just going to leave me with the square root of u du. So all my x's are gone, everything's in terms of u and du. That's what you want. The second thing that could happen, perhaps they don't cancel. Perhaps you still have an x involved in there somewhere, and it's not cancelling with anything, and you've got a u and you've got x, and it's just not looking nice. The only extra thing that you may be required to do is just rearrange the u substitution to get x equals. So this one's a bit ugly, but if it was the case and you had a random you had a random x in here somewhere, it's just a matter of saying, well, that's just u minus 1, and then it's squared, so I take the square root. And again, that is ugly, yes, but other questions it may not be. And you'll just make that last substitution for x equals in there to get rid of that last x, if you need. So I'll just reiterate, one of 2 things will ever happen. Your x's should completely cancel and be left with all u's du. If you have an x in there somewhere and it's not cancelling, rearrange the substitution line to get x equals and put that in there instead. All right, let's continue here. Now it's just a basic integration. You should know that's just the power of half du. So I'm going to add 1 to the power, divide by it, you'll get 2 on 3, u to the power of 3 on 2, plus c. The last step then is to make your substitution, to put it back in terms of x. All right, so then I'm just going to write this in a bit nicer way, 2 timesing by the square root of u cubed, and u being x squared plus 1 cubed, all on 3 plus c. So I should probably add that as a step, even though it's quite obvious, but step 5, sub in x. Okay? All right, so hopefully that helps there. Let's have a look now at a definite integral. There's one extra step in definite integrals that I'm just going to put in here. We'll call it step 3.5. And all it is change the bounds. So the reason is because on a definite integral, when we make everything in terms of u, our bounds here are still in terms of x, okay? As soon as you see bounds, you can turn them into x straight away. Now the substitution, which I haven't written yet, the question wanted you to use x equals tan theta. So I'm going to just start with step 1. Now I have an x and a theta. This should be an x. I'm differentiating x in terms, I see what I've done, u. I'm differentiating u in terms of x. Derivative of tan is sec squared x, you should know that. Now again, rearrange for dx equals. Hopefully you're getting better at this and can see that it's just going to be swapping them over to u over sec squared x. Okay. Step 3 is sub in my u and sub in my x. So I'm going to have 1 over 1 plus I see what's happening here. So using x equals tan theta, the question asked. So once again, same steps. I'm going to this time differentiate x with respect to theta. Okay, different terminology, but that's okay. And the derivative of tan theta is sec squared theta. Rearrange for dx, and I'm going to get sec squared theta, this time times d theta. All right, make my substitution. I get 1 over x is tan, so 1 plus tan squared timesing by sec squared d theta. So I've made my substitution for dx, and I know that x here is tan theta. Now, before I go any step further, my step 3.5. I know that x is equal to tan theta, so I now sub in these x values on my bounds. So I'm going to have tan theta equals 1 and tan theta equals 0. And I want theta values this time because I'm in terms of, that should be a theta, making that substitution. Hopefully you saw that. Because I'm all in terms of theta. So think about, when does tan theta equal 1? Well, straight away you should be thinking, hang on, I know my exact triangle. When you do opposite over adjacent, I get 1. So straight away theta is pi on 4. And tan 0 equals 0. You're either ever only looking at your exact triangles or you're looking at your graph. Okay, so tan of 0, well, tan passes through 0, so tan 0 is 0. So my other theta value is 0. Okay. I will do one more example where this could be a little bit trickier, but it's still doable. So now, one thing here, you should be familiar with the Pythagorean identity that says that 1 plus tan squared theta equals sec squared theta. So if you're not, recap your Pythagorean identities because they are important, which now gives me the integral of 1 over sec squared theta timesing by sec squared theta d theta. My secs are actually going to cancel. Remember, my new values are pi on 4 and 0. So now I'm just having the integral between pi on 4 and 0 of 1 d theta, which is just going to give me theta subbing in pi on 4 and 0. So my answer is just pi on 4. Okay, last and one of the more difficult U substitutions. And you'll soon see why. So it's a definite, okay? So let's start with my first steps. So I differentiate u with respect to x and rearrange to get dx equals. Now I make the substitution. So now I'm going to have x lots of u is 1 minus x minus du. Okay, a couple of things now. This is one of those examples which we were talking about earlier where I still have this floating x, which is bothering me because I need everything in terms of u. So that's where we just have to rearrange our original here, as our x's didn't cancel. So if I do rearrange this, I'll have that x is equal to 1 minus u. So I make that substitution there. 1 minus u timesing by u to the power of a half. Now I'm going to take the negative out the front of the integral, so I just have du. All right, hopefully you followed that okay. It is a bit trickier. All right, now always expand any brackets where this situation happens, okay? Expand them. Now I'm going to have u to the power of a half when I times that in there. Now u is really the power of 1. When I times two things, I add the powers, which is going to be negative u to the power of 1.5, which I write as 3 on 2, don't I? Du. Now my bounds, okay? So I have that u is equal to 1 minus x. My x values are at x equals 1 and x equals 0 on my bounds. So that's going to be u is equal to 1 minus 1 minus x, which is 1 minus 1, which gives me that u equals 0 there. And this one I'm going to have u is equal to 1 minus 0, which is going to give me that u is equal to 1. Now notice here, and really look at this. My bigger bound and my smaller bound pulled out the other way around when I subbed it in. So now my bigger bound is this one, my smaller bound is this one. I like to have the bigger bound on the top of the integral, but I can't just put 1 and 0 without any kind of repercussions. The rule is, when you flip the bounds, stick a negative out the front of your integral. Every single time. If you ever have to flip the bounds, you just stick a negative out the front of your integral and add that to your summary for this. Now, coincidentally, and doesn't happen all the time, but for this one I have a double negative now, okay? So my double negative will become a positive. Now I just have to integrate. So I'm going to have u to the power of a half, add 1, so I get 2 on 3, u to the power of 3 on 2. Okay, and this one add 1, which is really adding 2 on 2, so then I get 2 on 5, u to the power of 5 on 2, between 1 and 0. I am subbing in with some ugly powers there, so I'm just going to take one more line and say, well, that's really 2/3 timesing by the square root of u cubed, minusing 2/5 timesing by the square root of u to the power of 5. Much nicer. Now I can sub in my 1 and 0. I say, well, that's just 2 on 3 minus 2 on 5, and the rest is going to be minusing 0. And you still write the minus 0. So that's going to give me 10 minus 6 on 15. So my answer is just going to be 4 on 15. Okay, and there we have it. There's 3 different types of U substitution integrals.